For years, the electromagnetic railgun was hailed as the future of naval warfare, promising extreme speed and long-range strikes powered by pure kinetic energy. After more than a decade and over $500 million in development, however, the U.S. Navy halted the program due to barrel wear, massive power demands, and rising costs. To many, it seemed like a costly failure. But instead of scrapping everything, the Navy preserved its most valuable breakthrough, the hypervelocity projectile. Rather than the end of the railgun idea, it marked a strategic shift that could influence naval combat more effectively than the original system ever did. The $85,000 hypersonic round. The railgun's most impressive innovation wasn't the launcher, it was the projectile itself. The hypervelocity projectile was designed to survive the extraordinary electromagnetic forces inside a railgun barrel and travel at extreme speeds. When the launcher program stalled, engineers realized something important: the projectile didn't require a railgun to be effective. Instead, it could be adapted for use in conventional naval artillery. The U.S. Navy's Mark 45 5-inch gun, already installed on Arleigh Burke-class destroyers, became the unlikely platform for this high-tech munition. By pairing the HVP with a specially designed sabot that harnesses expanding gases from a traditional powder charge, the Navy could propel the projectile to speeds above Mach 5. Once it exits the barrel, the sabot separates and falls away, leaving the streamlined projectile to continue toward its target. Unlike traditional naval shells, the HVP isn't a simple ballistic round. It incorporates onboard electronics, guidance systems, and maneuverable fins that allow it to adjust its course in flight. Linked to the ship's fire control systems, it can receive targeting updates and execute high-G maneuvers in the final phase of its trajectory. This is where the strategic math shifts. A modern interceptor missile such as the SM-6 can cost several $1 million per unit. By contrast, estimates have placed the HVP's cost in the tens of thousands of dollars, around $85,000 per round in earlier projections. Even if costs fluctuate, the difference in scale is dramatic. Instead of firing multi-million-dollar missiles at every threat, a destroyer can now use guided artillery to counter cruise missiles, drones, and other aerial dangers at a fraction of the price. In recent sea trials, the Navy demonstrated that guided 5-inch projectiles could effectively engage aerial targets. With a firing rate of roughly 16-20 rounds per minute, a destroyer can create a dense defensive barrage, what some describe as a wall of hypersonic metal. The economic implications are profound. Modern warfare is increasingly shaped by cost-exchange ratios, how much you spend to neutralize what your adversary launches at you. If an enemy deploys relatively inexpensive drones or missiles, and you respond with interceptors that cost several $1 million each, you are fighting a financially asymmetric battle. The HVP helps rebalance that equation. The real limiting factor. If the railgun stumbled because of power requirements, directed energy weapons have long faced a similar challenge. High-energy lasers and microwave systems demand enormous electrical output, far beyond what older warships were designed to supply. This is where the Gerald R. Ford class aircraft carriers enter the picture. At the heart of each Ford-class carrier are two Bechtel A-1B nuclear reactors. While specific performance details remain classified, the Navy has confirmed that the A-1B design offers significantly greater electrical generation capacity than the Nimitz-class reactors it replaces. The Ford class was engineered not only to launch aircraft more efficiently using the electromagnetic aircraft launch system, but also to support future high-energy weapons. Unlike previous carriers, which allocated most of their generated electricity to propulsion and existing systems, the Ford class was built with substantial growth margins. This surplus electrical capacity makes it uniquely suited to host power-intensive systems such as high-energy lasers and advanced microwave weapons. In recent years, the Navy has fielded laser systems in the 30-150 kilowatt range aboard certain ships. Development is ongoing for more powerful systems, 300 kilowatts and beyond, with the long-term goal of fielding even higher output weapons capable of engaging increasingly sophisticated threats. The appeal is obvious. Once installed, a laser's cost per shot is extremely low compared to missile interceptors. While not literally $1 per shot when total system costs are considered, the marginal energy cost of firing a laser pulse is far lower than expending a multi-million-dollar missile. For defending against drone swarms or small boat threats, lasers offer a potentially game-changing solution. Instead of worrying about depleting missile inventories, ships could rely on systems limited primarily by power availability and cooling capacity. The Ford class was designed with this future in mind. The Carrier Killer Challenge. For over a decade, much attention has focused on China's anti-ship ballistic missile programs, particularly the DF-21D and DF-26. These systems are often described as carrier killers, intended to threaten large surface vessels at extended ranges. Intercepting such weapons is extremely challenging. Ballistic missiles travel at high speeds, and defending against them requires layered systems, early detection, tracking, and interception during various phases of flight. Traditionally, this has meant relying on advanced interceptors such as the SM-3 and SM-6, which come at considerable cost. Here again, the Navy's evolving approach reflects a layered philosophy. Rather than relying solely on expensive interceptors, ships may combine kinetic defenses like guided projectiles with directed energy systems. Hypervelocity projectiles could potentially engage certain classes of aerial threats at shorter ranges, while lasers might be used in terminal defense roles against drones or other inbound systems. It's important to temper expectations. Defending against high-end ballistic or hypersonic threats remains technologically demanding, and no single system provides an impenetrable shield. However, by diversifying defensive tools, combining missiles, guided artillery, lasers, and electronic warfare, the Navy aims to complicate an adversary's calculations. Instead of a single expensive interceptor for every incoming threat, a ship might deploy a spectrum of responses optimized for cost and effectiveness. The objective is not merely to survive a saturation attack, but to make such an attack economically unsustainable for the adversary. The next generation, DDGX. Looking ahead, the Navy's future large surface combatant, commonly referred to as DDGX, is envisioned as more than a replacement for aging Arleigh Burke destroyers. It is expected to feature an integrated power system capable of flexibly allocating energy between propulsion and onboard systems. Integrated power architectures allow ships to divert electricity where it's needed most, whether that's driving the propellers or feeding high-energy weapons. This flexibility is essential if lasers in the 300 to 600 kilowatt range or beyond are to become operationally viable at sea. While speculation sometimes extends to megawatt-class naval lasers or entirely new energy dreadnoughts, the reality is more incremental. The Navy is steadily scaling up power, cooling, and beam control technologies. Each increase in output opens new defensive possibilities. At the same time, research continues into high-power microwave systems designed to disrupt or disable the electronics of drone swarms. Unlike lasers, which must dwell on a target to inflict thermal damage, microwave weapons can potentially affect multiple targets simultaneously within a cone of effect. The combination of guided kinetic munitions, lasers, and microwaves represents a layered system of systems approach. No single technology dominates, instead, they complement one another. The economics of modern naval warfare. At its core, this transformation is about economics as much as physics. In recent conflicts, militaries have confronted a growing mismatch: inexpensive drones and loitering munitions versus costly interceptors. When a $20,000 drone forces the launch of a $2 million missile, the defender loses financially even if the target is protected. The Navy's adaptation of the hypervelocity projectile and its investment in directed energy systems aim to reverse that imbalance. Guided artillery rounds that cost tens of thousands of dollars and laser pulses powered by onboard reactors change the cost curve. Of course, development, integration, and maintenance of advanced weapons systems are not cheap. Total program costs must be considered. Yet the marginal cost of engagement, the price paid each time a weapon is fired, matters enormously in prolonged or high-intensity conflicts. If future naval combat becomes a contest not only of firepower, but of endurance and industrial capacity, the side that can defend itself at lower per-shot cost gains a strategic advantage. The future of warfare isn't just about bigger weapons, it's about smarter technology, cheaper defense, and the power of pure energy changing the battlefield. If you want to stay ahead of the innovations shaping tomorrow's world, make sure you follow the channel. And if you want to be smarter every day, like and subscribe.